So what are complex numbers? Complex numbers arise from the fact that the square root of -1 is not a real number. It's an imaginary number, and so we call that I. Now, this leads to the fact that I squared is -1, and this is essential to understanding the way complex numbers work. Also, when we talk about complex numbers, they have a standard form. That standard form is A plus bi, where a is the real part and bi is the imaginary part of the number. When solving a problem like this one, it's really key to realize that I is treated just like a variable. It's treated just like x, with the only difference, when I put it down here in the corner, that our answer is going to be in the form a plus bi, so we're just going to answer with the I towards the end. So the first thing I'm going to do is distribute the negative sign into these terms. So it's going to be 3 plus 2 minus 3i. And since it's a plus sign, I can just get rid of the parentheses and make that -5 plus I. Now, combining like terms, all the real numbers, I have 3 plus 2 minus 5, which gives me 0. And for the imaginary parts, I have -3i plus I, which gives me -2i, which is in the form a plus bi, and we just typically don't write the 0, so the answer to this would be -2i. When solving this problem, we're going to distribute all the terms out and multiply them out just as if it was an x. So I'm going to have 8 plus 6i minus 4i minus 3i squared. Then I can combine some like terms. 8 plus 2i minus 3i squared. And we need to remember from the previous ones that I squared is -1. So I'm going to replace that with -1. And so that's going to give me 8 plus 2i plus 3, because -3 times -1 is +3, which gives me an answer in standard form of 11 plus 2i. To solve this problem, first remember that anything squared means multiplying it by itself. So let's write that out so we're not tempted to distribute that. 4 times 4 is 16. Minus 4i is minus 8i minus I squared. And once again, I squared is -1, so I'm going to replace that I squared with -1, which is going to be minus -1 or plus 1, which gives me an answer of 17 minus 8i. So this problem says to multiply by the conjugate, and the complex conjugate of a plus bi is a minus bi. So you're just taking the opposite sign of the imaginary part. So for this problem, take 4 minus 2i times 4 plus 2i. Notice that it's a very similar pattern to the difference of squares, which is really the whole point of them. And so I get 16 plus 8i minus 8i, and that's very key. Those terms will cancel. And the last term is minus 4i squared. Again, I squared is -1, so let's replace the I squared with -1. I have 16 then plus 4 for an answer of 20. Now this is the whole purpose of the complex conjugate, to get rid of the imaginary part and give us simply a real number. If I want to write this fraction in standard form, I need to get rid of that denominator. I need to make something sort of normal down there. I need to make a real number. And it's similar to rationalizing denominators with square roots. So I'm going to multiply by the conjugate, the complex conjugate of the denominator. So in this case, that is 2 plus I. And so the numerator, I have 2 plus I as well. So I'm really only multiplying the whole expression by 1, so I'm not changing it. So in the numerator, I have 10i plus 5i squared. In the denominator, I have 4, the pattern difference of squares, that the I terms will cancel out, so I have 4 minus I squared. So simplifying the I squareds to -1 here and here will give me 10I minus 5 over 4 plus 1. So I'm going to change the order around again for standard form. Give me negative 5 plus 10I over 5. And that's still not quite standard form. I'm going to distribute that division to simplify things. Negative 1 plus 2I. First thing you should notice in this problem is, first of all, obviously multiplication, but also that I have a square root of a negative number. So instantly, when you see the square root of a negative number, make that I, because it really means the square root of negative 1 times the square root of 5, and the square root of negative 1 times the square root of 20. Square root of negative 1 is I, and I, square root of 20. Now multiplication is associative and commutative. I can put these numbers in any order. It's all multiplication. So I'm going to multiply I squared, and I'm going to multiply 5 and 20 to get 100. I squared is negative 1, and the square root of 100 is 10, so my answer to that is negative 10. When you first see a problem like this, you might instantly think, okay, let's factor this. And you might try once or twice and you realize it's not factorable, so we're going to use the quadratic formula. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Plugging in my values, x equals the opposite of b, 2, plus or minus the square root of negative 2 squared, or 4, minus 4 times 1 times 2, all over 2, which is 2 plus or minus the square root of 4 minus 8 over 2, 2 plus or minus the square root of negative 4 over 2, and here's where the difference comes in. That square root of negative 4 is obviously an imaginary number. So I have 2 plus or minus, that's going to be 2i over 2, and I'm going to distribute the division here again, 1 plus 1i, or just simply 1 plus I, and plus or minus I, and that is my answer. When looking at this problem, you could go ahead and use the quadratic formula, but since there is no linear term, since there's no term with x to the first, how you could sort of easier do it is take x squared equals negative 64, subtract 64 from both sides, and now I can take the square root. Now, since I'm introducing a square root, I absolutely have to put plus or minus. And it's a plus or minus the square root of negative 64. So I have plus or minus the square root of the negative gives me an I, and the square root of 64 gives me 8. So I have plus or minus 8i. Again, since we introduced the square root, it was not there originally in the problem, we must have plus or minus. This is a relatively straightforward distributive property. Negative 2i times 5 is negative 10i, and negative 2i times negative I is positive 2i squared. Now again, remember, I squared is negative 1, so I have negative 10i minus 2, but that's not good enough. That is not standard form. It's not a plus bi, so I just switch the order of the terms. Negative 2 minus 10i. For math true and false problems, one approach is to attempt to prove it false. If you can come up with a single case where it's not true, then it's automatically false. It's much easier to come up with a single counterexample than to find every single solution that's possible. So this one says that the sum of two imaginary numbers is always an imaginary number. Now always is, right away, that's a term we want to be careful about. So it says I'm adding two imaginary numbers. Now adding includes subtraction. So I can add negatives, for example. And then I'm saying I'm always going to get an imaginary number. So I'm saying I take some term plus, I'll use another term, ci, is it always going to be an imaginary number? And instantly I think, well, there's the case that if I take, say, 2i and I add negative 2i, they're different numbers. B is 2, c is negative 2. I'm adding, the sum of that is 0, which is not an imaginary number. Therefore, I have just proven that this statement is false.